Chapter 18 is going to be about ketones and aldehydes. First, let's talk about the classes of carbonyl compounds. You can see here the different functional groups of the different carbonyl compounds. This chapter we're going to learn about ketones and aldehydes, and then in the next few chapters we're going to learn about carboxylic acids and the derivatives of carboxylic acids, which are acid chlorides and amides and esters. But mostly in this chapter is going to be ketones and aldehydes. So the structure of the ketone, we already know this. It's trigonoplanar in shape. It's 120-degree bond angles. You have a sigma bond plus a pi bond between your oxygen and your carbon with two lone pairs. This just kind of just shows you that a carbonyl bond is actually stronger than a double-double carbon bond. It's stronger because you have more electronegativity of the oxygen, so it like pulls the carbon closer to it. So this bond is actually shorter. This overall length between the two atoms is shorter than the length between two carbons. You can see that by 0.1 angstrom, which in the atomic world is pretty big. And then energy-wise, you can see that it's almost 130 kilojoules per mole higher in energy. You don't need to know these numbers, just know that the bond is a little bit smaller and it's a little bit higher in energy. Okay, so we also know it's sp2 hybridized, so the carbonyl bond is shorter, stronger, and more polar than the CC double bond in alkenes. Carbonyls do have a resonance structure, though we don't write this as the minor this is the minor form of it, and the reason is because you don't have an octet on your carbon. Alright, you want to have everything octet, so this is technically the major form, but this is kind of helpful to kind of show you how carbonyls react. You can see that carbonyls, you have a partial positive charge more on your carbon. We kind of write a partial positive, and the partial negative on the oxygen, so you've got a dipole going towards the oxygen, but this kind of resonance structure just kind of shows it to you more. It kind of shows you it's more polarized. Okay, so like I said, the first resonance structure is better because the octet and there's no charges. The carbonyl has a partial positive and will react with electrophiles. Actually, that is incorrect. The carbonyl compound has a partial positive and will react with nucleophiles, not electrophiles. Nucleophiles. Okay, your oxygen can act with electrophiles because it's partial negative. All right, naming, ketone naming, and we'll talk about aldehyde naming second. Ketone naming, there's an older version where the number, we've already talked about this, the number is in front of the name rather than the number being in the name. This is the newer way of doing things. This is the way that we're going to kind of do it now, but you should be aware of the older naming, so this is kind of the new way of doing it, where the number goes in between the name rather than the number going in front of the name. Okay, and you name this just like everything else. Your carbonyl is your parent, so you start counting on the side closest to the side of your functional group. So we start counting on this side. On this one, it doesn't matter which side you start on, it's equal. All right, and then we'll talk about this one in a second. So it's 4 carbons, so it's a butane, and then at the second carbon I have my carbonyl, so that's your 2, and ended in -one because we are with ketones. All right, this one here is your longest chain of the 5 carbons, and you've got a methyl and a methyl as your functional group. So you have 2,4-dimethyl. All right, it's 5, so it's pentan. The carbonyl's on the 3rd carbon, 3-one. All right, now for this one, we talked about naming aromatic rings. There's 2 ways of naming it, where the aromatic ring is the parent compound, or the chain is the parent compound. In this case, the chain is your parent compound. All right, and the aromatic ring is a substituent hanging off of your chain. This is carbon 1 because it's the carbon with the carbonyl, and your phenyl ring is hanging off of carbon 1. So 1 phenyl, right? Propan, 1 one. Okay, so the phenyl group in this case is a substituent. It's not a parent. Okay, so basically this says exactly what we just talked about. Cyclical ketones, your carbonyl is always carbon 1. All right, I think we might have briefly discussed in class that if you have more than one functional group on your compound, like here, for an example, I have a double bond and a carbonyl, which one gets the priority? Well, the more oxidized your functional group, the higher the priority. So here's a perfect example. You have an alcohol and a ketone. Well, your ketone is more oxidized. There's more bonds to oxygen than there is to the alcohol, so this becomes your parent. This is your parent. In this case, it's pretty easy. This is the only functional group you have, so that's your parent. But on ring compounds, this is always carbon 1. Start going the side to the closest substituent. So 3-methyl, all right, cyclopentanone, all right. Notice you do not have to put the name or the number of your double bond because, I'm sorry, of your carbonyl, because your carbonyl is always carbon 1, okay. In this case, they kind of want you to do it because it's called an enone. Okay, so the ene is on carbon 2. It would look weird if it was cyclohex-2-enone. All right, so that's why you put the 1, but that's kind of redundant. Okay, it's always number 1, but in this case, if you have another functional group, you do it. All right, but in this case, if this is your only functional group, then you don't have to say it because that is always carbon 1. All right, so in this case, this is our functional group, or our parent functional group. There's the longest continuous chain. All right, this is a hydroxy group, and this is a methyl group. This is alphabetically first, so 4-hydroxy, 4-methyl pentantuone. All right, and basically this is going to say exactly what I said. The cycloketones, the carbonyl is always number 1. When the compound has a carbonyl and a double bond, the carbonyl takes precedence. You know, again, it's because it's more oxidized. Aldehyde nomenclature, just as easy, except this time aldehydes end in al. Okay, this time you don't have to put the number in. Ketones, you had to tell me what carbon the carbonyl's on, but in this case you don't, and it's for obvious reasons. Your aldehyde is always carbon 1. It's always at the end of the chain. That's what makes an aldehyde an aldehyde. Your carbonyl is at the end of the chain. So aldehydes are always carbon 1. So you never have to say, you know, heptan 1-al. It's always 1-al. Okay, notice in every case you do not have a 1 in any of the cases. Right here, notice you have an enal. You don't have 2-en-1-one like we did in the last example, where you technically don't have to do it in a cyclical compound. But in this case, you don't have to do it. It's an enal. So ethanal. Sorry, I pronounced it incorrectly. Ethanal. All right, longest continuous chain with your carbonyl. And then you have your substituents. Bromo comes before methyl, so 4-bromo, 3-methyl heptanal. All right, here you have a hydroxy. Once again, this is a higher oxidation, so that will get the priority. So 3-hydroxy butanal. This is an enone again, 2-pent-2-enal. Okay, notice you don't say the 1. It's not 2-en-1-al. All right. This case is a little different. This case, if you just have a CHO, okay, so remember it's kind of shorthand. It's just a CH, and then you have some other kind of weird group to it, which is easy to name by itself. Okay, you now start naming this as a carbaldehyde. Okay, so when you just have a single carbon hanging off of another chain, it's called a carbaldehyde. All right, so this is cyclohexane carbaldehyde. Okay, in this case, it's kind of like this is our parent, yet we're going to name it as if this is our parent. It's a little strange. Only on these cyclical compounds do we do this, because they hang off of our cyclical compounds. Okay, so it's always carbon 1. Again, you're naming the most oxidized group, so it's always carbon 1. So 2-hydroxy cyclopentane 1-carbaldehyde. Okay, I hope that makes sense. Okay, aldehyde carbon is 1, replace the E with al. If the aldehyde group is attached to a ring, you always use carbaldehyde, and it's at the end. All right, carbonyls as substituents. So what happens this time if you have another functional group that takes priority, or if you have 2 carbonyls? Okay, so here's an example. We have a ketone, we got an aldehyde. So what we've always learned is if you have a tie, all right, or if you have 2 groups that are similar, start with the one that's closest to the end. In this case, my aldehyde. So the aldehyde's going to get the priority. So what do we name this? This is now a substituent hanging off of my longest continuous chain. Okay, so this is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. At the 3, I have an oxo. So carbonyls are called oxos if it's a substituent. Okay. So this is called 3-oxopentanal. All right, let's go to this one before we go to this one. This is kind of a weird one. But in this case, we have a aldehyde, a ketone, and then carboxylic acid. So which one's more oxidized? Your carboxylic acid. That's why it gets the priority. Now, they kind of throw this in here. We haven't learned how to name carboxylic acids. We will in the next chapter. But basically, you end in oic acid. Not too challenging. So carbon 1, carbon 2, carbon 3, carbon 4. At carbon 3 and carbon 4, I have oxos. You don't have to distinguish between an aldehyde or a ketone. It's just basically a carbonyl. So the reader will figure out one of them is a ketone and one of them is an aldehyde. So 3,4-dioxobutanoic acid. For aromatic rings, first of all, if you just have an aromatic ring with a carbonyl, an aldehyde carbonyl, that's called benzaldehyde. Okay? Now, so I have a benzaldehyde, but I have a carboxylic acid, which gets priority. So this is my parent. Okay? In this case, remember in the last page we called it a carbaldehyde? Okay? Is that what it was, carbaldehyde or carboxaldehyde? A carbaldehyde. Well, that's if it's hanging off of a non-aromatic ring. If it's hanging off of an aromatic ring, you call it a formal group. Right? Formal is short for a one-carbon carbonyl. Like, for example, this is called formic acid. That's formic acid. This is formaldehyde. Okay, that's where the form coming. It's kind of a common way of naming one-carbon fragments. So formaldehyde, formic acid, this is a formal group. Okay, so you would name this 2-formal benzoic acid. I have seen it called 2-carbaldehyde benzoic acid, but they obviously don't want us to use that as the naming. Okay, so any molecule with a higher priority functional group, a ketone is an oxo, and an aldehyde is a formal if it's on an aromatic ring. Okay, aldehydes have higher priorities than ketones. That's just because the order of the order at which it falls on the molecule. Now, there's some common names for ketones. Okay, there's only probably one here that I want you to know, and that's the methylethyl ketone. For short, actually, people call it MEK. That's kind of the industrial name, MEK. It's used as a solvent, but rather than calling it what we call it, 2-butanone, people just call it methylethyl ketone, meaning methyl ethyl ketone. Here, disec-butyl ketone, just easy just to name the two groups on either side. Okay, this is they call it beta rather than what would it be, 1? You know, it'd be 1-bromo. Sorry, 1-bromo, 4-methyl, you know, so forth and so on. There's 4-bromoethyl, name that group. Isopropyl, name that group. Ketone. So it's kind of the common way is to name this side and then to name this side and then say ketone. Okay. Another common one, which we will see, I think, in the next few slides, but since we're talking about it, is this one. That you should know the name of that one. That one is acetone. Okay. So just a common name. So here we go. Here it is. Here's acetone, acetophenone. All right. These are some common names. Benzophenone. Like I said, we saw this on the last page. This is kind of common names. You don't really need to know these. You know, I would, you should probably know acetone, acetophenone, and benzophenone. Those are kind of common ones. All right, so that's naming compounds.